In this part, I'm going to explain elimination reaction. High temperature favor elimination over substitution. In elimination reaction, the substrate should have at least two carbon atoms. The carbon to which halogen or the leaving group is attached is called alpha carbon, and the carbon directly attached to the alpha carbon is called the beta carbon. The alpha carbon may be attached to 1, 2, or 3 beta carbon. In elimination reaction, the leaving group departs along with its bonded electrons from the alpha carbon. A base interacts with the hydrogen, or better if we say a proton, from a beta carbon, leaving the bonded electrons to interact with the empty p orbital of the alpha carbon, forming a pi bond with it. The product after reaction has both alpha and beta carbon sp2 hybridized, while the substrate had both these carbon atoms sp3 hybridized. The study of reaction kinetics of elimination reaction reveal that the reaction kinetics may follow both first order and second order kinetics, just similar to nucleophilic substitution reaction. When the reaction rate is following the first order kinetics, it is proportional to the concentration of the substrate only. The reaction mechanism is a two-step reaction. The first step is formation of carbocation, which is slow and rate determining. The second step is attack of base, which is fast. This is called E1 reaction, and the energy profile of E1 reaction is like this. Tertiary alpha carbon, or simply tertiary alkyl halides, favor E1 reaction because, as we all know, that tertiary carbocation formed in the first step is most stable. The animation may be shown like this also. Regio-selectivity of E1. Consider this, which form a tertiary carbocation in the first step. Now here there are 3 beta carbon. All 3 beta carbons have hydrogen bonded and so capable of interacting with base. When hydrogen from these 2 beta carbons interact with the base, we get a disubstituted alkene as the product. When hydrogen from this beta carbon interact with base, we get a trisubstituted alkene. Since the trisubstituted alkene is more stable, it is the major product. This is called ZAITSEV'S rule. Stereo-selectivity of E1. The best example is perhaps the elimination of 1-phenyl propan-1-ol under acidic conditions. First, the OH group is attacked by a proton and turned into a good leaving group. Then the carbocation is formed. This is the alpha carbon, and there are 2 beta carbons which are directly attached to the alpha carbon. This beta carbon has no hydrogen attached to it, and this beta carbon has 2 hydrogen atoms attached to it. The carbon-carbon bond is free to rotate. When this carbon-hydrogen sp3 bond is in line with the empty p orbital, then the base attacks the proton because the bonded electrons can easily engage with the empty p orbital to form a pi bond. The product is a Z alkene. When the other carbon-hydrogen sp3 bond is in line with the empty p orbital, then the product is E alkene. Here E alkene is the major product because it is less sterically hindered than the Z alkene. E1 with carbocation rearrangement. See this compound 2-chloro-3,3-dimethyl-butane. When heated, this leaving group departs, forming a secondary carbocation. Now the base attack the hydrogen on beta carbon to form a monosubstituted alkene. Or there is a methyl shift from the carbon next to it because it gives a more stable tertiary carbocation. Then the base react with this hydrogen of the beta carbon, which give disubstituted alkene. Or the base may react with this hydrogen of the other beta carbon to form a tetrasubstituted alkene. Out of the three products, this one is the major product.